Welcome to this session. We introduce the concept of differential equations. So we start by defining what we mean by a differential equation, and then discuss how we classify a differential equation. Now we start by defining what we mean by a differential equation. So an equation containing the derivatives of one or more unknown functions with respect to one or more independent variables is called a differential equation. So that's how we define a differential equation. But the next thing we discuss about how we classify differential equations. Now we can classify differential equations according to type, order, and linearity. So type, and then number 2, order, and then number 3, linearity. So let's start with the first type of classification, or first class of classification, which is classification by order, classification by type. So majorly, there are two types of differential equations, what we call ordinary differential equations and partial differential equations. So there are two types of differential equations. Namely, ordinary differential equations what we call ODEs, and then partial differential equations. So called the PDEs. So definition of an ordinary differential equation. So if a differential equation contains only ordinary derivatives of one or more unknown functions with respect to a single independent variable it is said to be an ordinary differential equation. Abbreviated as ODE. So examples. So we can have dy dx plus 5y equals to e raised power x. Or we can have d squared y dx squared plus 4 dy dx plus 6y equals to 0. Or we can have dx dt plus 2 dy dt equals to 2x plus y. Or we can have number 4, d squared x dt squared plus 6x equals to 0. So all these are examples of ordinary differential equations because of presence of these ordinary derivatives. And then let's define what we call by term PD. So an equation involving partial derivatives of one or more unknown functions of two or more. Remember, the ordinary is one, but this one is two or more independent variables. Is called a partial differential equation. Abbreviated as PDE. So examples of PDE: one, partial squared u partial x squared plus partial squared u partial y squared equals to 0. This is actually what is called Laplace equation in 2D. Partial squared u partial x squared equals to partial squared u partial y squared plus 2 partial squared u partial t squared. And then number 3 example, partial squared u partial x squared equals to partial squared u partial t squared minus 2 partial u partial t. Number 4, partial u partial y equals to negative partial v partial x. Number 5, and half partial squared phi partial x squared plus partial squared phi partial y squared plus partial squared phi partial z squared equals to 0. This is the Laplace equation in 3D, etc. So presence of this kind of derivatives, or say this kind of derivatives, or say this kind of derivatives, are so-called the partial derivatives, is what defines partial differential equation. Now let's see the second way of classification of differential equations. So 2, classification by order. So the order of a differential equation is the order of the highest derivative in the equation. So definition: the order of a differential equation is the order of the highest derivative in the equation. So in form of an example, states the order of the following. So A, d squared y dx squared plus dy dx equals to x. B is dx dt equals to xt power 6. Let's start with these two examples. Now, for this first differential equation in A, so the highest solution, the highest derivative is d squared y dx squared, a second derivative, so the order is therefore 2. So this is a second order differential equation. And then in the second one, B, the only derivative appearing is dx dt, a first derivative, so the order is therefore 1. Another example, if we have C, L d squared q over dt squared plus R dq dt plus q over C equals to E sine omega t. Now, since the highest derivative is 2, so this is also of order 2, for this is the highest derivative appearing here. And then C, if we have cos x d squared y dx squared plus sine x dy dx power 4 plus 8y equals to tan of x. Now, remember that this is a second order derivative. This is a first order derivative, but this first order is raised to power 4. But we have defined the order to be the highest derivative in the differential equation. So therefore, this still is a differential equation of order 2. And then this is dE. If we have 1 plus dy dx power 3 raised to power 5 equals to d squared y dx squared raised to power 2. Now remember this first order raised to power 3, this second order raised to power 2. So the key thing here is that the highest derivative is this second order derivative. So this is also an order 2 differential equation. Now let's define what we call by degree. So definition. So degree of a differential equation, degree of a differential equation is the power of the highest derivative occurring in the differential equation. So for instance, if we have, so state example, one, if we have L d squared Q over d t squared plus R dq dt plus Q over C equals to E sine omega t, then the highest derivative in this differential equation is this one, this second derivative, but the power here is 1. So the degree of this equation is degree 1. Number 2, if we have cos x d squared y dx squared plus sine x dy dx raised power 4 plus 8y equals to tan of x, then this is the highest derivative occurring in this equation. So the degree will be determined by the power of this second derivative, and this is still 1. So this is also degree 1. So don't confuse with this power 4 because this dy dx is a first order derivative, while we have the one that has second order derivative. So what determines is the power of the highest derivative occurring in the differential equation, not just any power of the derivative in the differential equation. Number 3, if we have 1 plus dy dx squared power 3 equals to d squared y dx squared power 2, then since this is the highest derivative, the power is 2, so this is a differential equation of degree 2. Next session we'll discuss about third classification according to linearity of a differential equation.